Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and in this module, as discussed last time, we will be introducing the concept of scalars, vectors and tensors, and let us begin. So quickly, what are scalars? Now we are going to talk about, I think these are fairly trivial concepts, but we'll be talking about these concepts from the point of view of the tensor algebra. So scalars are quantities which will remain invariant when we transform from one coordinate system to the other, right? So these are real numbers. So let phi be a real number, and then they are defined. Suppose they are defined in a coordinate system, then phi is said to be a scalar. So phi is a scalar if it has the same value in every coordinate system, right? So that is for any pair phi prime is equal to phi. So for any pair phi prime is equal to phi, right? So the value doesn't change when we change from one coordinate system to the other, then those real numbers are scalars. Now for a vector we have the change will be described in terms of the coordinate matrix of coordinate transformation. So suppose v1, v2, v3 are set of three real numbers, right? So three real numbers defined in a coordinate system, right? So then v1, v2, v3 are components of a vector if their values in any pair of the coordinate transformation C and C prime are related by V prime equal to AV, right? So we have that the matrix A is given by so this is how the vectors are related. So this is our the transformation matrix, right? As we saw, the transformation matrix from C to C prime. Now similarly, we can now describe what are tensors. So what we can say about tensors? So let Tij where I and j are between 1 to 3, so this is in three-dimensional space, be a set of 9 real numbers, so defined in any coordinate system, right? And then we can talk about the components in another coordinate system. So then we call these Tijs are a second order tensors, if their values in any pair of coordinate systems are related as follows. Are related as Tij prime is summation k from 1 to 3, L from 1 to 3, Aik, Ajl, Tkl, right? And we see that so similarly, so this is for a second order tensor, right? And then we can similarly describe a third order tensor. So for a third order tensor, we have the following relation holding. So Tijk prime can be written, so this is in the coordinate C prime. So this is k from 1 to 3, j, well, and m from 1 to 3 and n from 1 to 3, ail, ajm, akn, tlmn, right? And so this is how the third order tensors are related. So there are 27 components in total, 3 cross 3 cross 3. Now one thing in all our discussion, we will not adopt a summation notation. So what I mean is, so the summation convention is aij bj is summation aij bj. So this is not going to be not adopted, right? So we have that Tij prime is summation k from 1 to 3, summation L from 1 to 3. We see that this is, I'm trying to write this tensor in a matrix vector multiplication form. So this is Tij prime is aik, ajl, tkl. So this is summation L from 1 to 3, summation k from 1 to 3, aik, tkl, ajl. And then this is also equal to summation L from 1 to 3, summation k from 1 to 3, aik. So what has happened is, well, aik, tkl, and then from L we switch this notation alj, but this is transpose now. So now if we rewrite this, so notice this indices, we are going to follow these indices and rewrite this in matrix vector form. So this is going to be A transpose, right? So our new matrix T prime is going to be A transpose. So this is how a second order tensor is defined via the matrix of coordinate transformation A. So second order tensor, right? So then what we have is that let us look at some examples. So suppose we look at a second order tensor. So in coordinate system C, system C, our tensor T is given by 1, 4, 7, 2, 5, 8, 3, 6, 9. So this is our tensor T. So the problem says we have to find the components. So find the components in C prime if C prime is obtained from C, by a rotation of 90 degrees about the OX3 axis. So that's how we obtain the new coordinates. So of course our matrix transformation is 0 1 0 minus 1 0 0 and 0 0 1. This is something we had seen few examples back. And then the second problem says if the transformation matrix is obtained via reflection in the x3 equal to 0 plane, and in this case the matrix is going to be x3 equal to 0 plane will be the x1 x2 plane. So we will have 1 0 0 0 1 0. So x1 x2 are undisturbed, but x3 becomes 0 0 minus 1. Okay, so that is our new matrix A. Okay, so then our matrix T prime in this case will be A. Well, we want to find what is T prime here, right? So this is when, the answer should be fairly clear. So I don't even have to write. So all these matrices are known, we can find the answers. Okay, so then we talk about some special types of tensors which also are invariant along various coordinate axes. Scalars are always invariant. How about tensors? So it turns out that certain class of tensors are also invariant. They are so called the isotropic tensors. So one example is the identity tensor. So we see that if we look at the identity matrix I, so we see that A transpose IA is A transpose A, IA, and this is equal to identity because A is a unitary matrix. So any coordinate matrix of coordinate transformation when acted on I will give you only I, right? And we see that in this case the tensors, so identity is one such matrix where it remains unchanged when the matrix of coordinate transformation is applied. So we call these special tensors as isotropic tensors, which show this property that they are unaffected by the matrix of coordinate transformation, and it turns out that these are always scalar multiples of the identity matrix. In fact, this result can be proved, which we leave it to the readers, to the listeners. Okay, so at this point, let us now also describe another type of multiplication, or the so-called matrix outer multiplication, outer product multiplication. So tensor algebra. So let us look at the matrix outer product, right? So suppose Uijk is a second order tensor, right? So this is a second order tensor, which means it has 27 components, and Uij is a second order tensor, so it has 9 components, and we have Vijk, this is a third order tensor, so this has 27 components. Then we can describe a fifth order tensor, so Ijk Lm can be described as the product of these tensor components, Uij V KLM, and this is a fifth order tensor. This is a fifth order tensor, and so we can see there are 5 indices, which means that there will be 3 to the power 5 terms in this tensor. Now, so we call these typical multiplications as outer products, because here in outer products the order of the tensor always increases in comparison with the multiplicating tensors. Now there is also so So let us look at an example. Say for example, if you have a vector ui and vj, and these are of course tensors of order 1. So these are vectors, tensors of order 1. So then you have that ui vj is a second order tensor, and we get that this is equal to u1 v1 u1 v2. So all possible multiplications are clubbed in this ui vj. So u1 u3, and then similarly u2 v1 u2 v2, and so on, and we will have 9 components, and so on, u3 v1, and so on. So then we can also talk about contraction operation of a tensor, right? The contraction operation. So it turns out that the outer product increases the order of the tensor, the contraction decreases the order of the multiplicative tensors. So how is it possible? So contraction of tensors. So suppose Tijkl is a fourth order tensor, and let us say we take indices. So we select 2 indices, k and l, right? And then we set them as equal and set them equal. So now our tensor now is Tij, let's say mm. So we know that whenever we have repeated index, it means that we are summing up over this repeated index. So this is Tij mm m from 1 to 3 in 3D space. So which means now this is going to be a second order tensor. So from this example, we can learn that the moral of the story is that the contraction reduces the operation or the order of the tensor by a factor of 2. So we have that. So reduction in the tensor order by a factor of 2, right? So now suppose we have a trace. What is the trace of a matrix? So we see that the trace is let's say second order tensor Tij. So trace is Tii. So Tii means T11 plus T22 plus T33. So these are all the sum of the diagonal elements, and this is of course a scalar or a 0th order tensor, right? So certainly for a second order tensor, the trace, which is the contraction operator, reduces the order by 2 and it becomes a scalar. So then it turns out that trace also has more special properties. For example, this is also, being a scalar, it's going to be invariant under transformation, invariant under matrix transformation, right? So then let us talk about, so I think in terms of the background, the tensor formulation background, I am very much done. And now let us slowly start into our induction of these ideas into the physical aspect of our discussion of classical mechanics. So we start with the angular velocity. So our angular velocity, so revisiting all these ideas, angular velocity ideas, in the tensor form. So the angular velocity omega is defined to be a vector that gives V is omega cross R, or we have V is equal to omega x, right? So if we rewrite this angular velocity in the tensor form, so our translational velocity is omega cross R, so in the cross product notation, and now our angular velocity components v1, v2, v3 is 0 minus omega 3, omega 2, omega 3, 0 minus omega 1, and so this is, well, let me write and then I'll say that minus omega 2, omega 1, 0, and this is x1, x2, x3, right? And we see that if we were to write this v in the omega formulation, omega xi's, then well, in this dot product notation, this has this following matrix which satisfy this cross product identity as well. So this is the matrix of the angular velocity. So of course this is a second order tensor, and we call this as omega double bar. So we denote a double bar over omega. So this is the second order tensor. Okay, so then let us now also talk about, so this was the angular velocity tensor. Our next is the moment of inertia tensor, right? So we talk about the inertia tensor in general. We will see how the inertia tensor gives us the moment of inertia. So inertia tensor. So we saw that, recall what is the formula for angular momentum. Angular momentum of a rigid body about, let's say, a fixed point O. Angular momentum of a rigid body about O is defined by L naught is given by summation Ri cross Mi Vi, right? So this is R cross Mv, and V is omega cross R. V is omega cross R. And so now let us substitute the value of V here. So we see that, so what have we got? So this is, so L, so which means L naught is R cross M times omega cross R. Omega cross R, and then this is also going to be M times, so we take the cross product here. So R dot with R omega minus R dot omega R, right? And then we see that this is also equal to summation K from 1 to 3 xk times xk omega I minus xj omega j times xi, right? So so this is my this is the expanded version of this dot product, vector dot product in the summation notation. So notice that this is again, let me call that, rewrite this. So this is also equal to summation xk, and this is omega, this is, I'm writing it in terms of delta notation here. So this is summation delta ij omega j minus summation xj omega j xi, right? So summation j from 1 to 3. So xj omega j xi. So then this is also equal to summation j from 1 to 3, and I'm going to take omega j out of our equation here, and we see that this is summation over k xk, right, and delta ij, so the j summation is gone, minus xi xj, whether xj xi or xi xj, it's the same, and times omega j, and we see that now angular momentum is equal to this quantity, which is our the so-called inertia tensor. So this is j from 1 to 3 iij times x times omega j. So this is our moment of inertia tensor. So then what we have is that this is the inertia tensor. So this is the inertia tensor. This is the inertia tensor in general. Now I want to show where is our moment of inertia. So it turns out that the moment of inertia are all the diagonal elements of this inertia tensor. So let us now try and look at some quantities out of this. So for example, our angular momentum is L naught given by summation Ij omega j. This is I dot omega. So this is our angular momentum, and our kinetic energy in terms of the inertia tensor is given by half omega transpose I omega. Now I have to put a bar on top of this I, or a double bar, I would say. Let me put a double bar. So this is an inertia tensor I double bar, so that I don't confuse this I with the identity matrix. So we put a double bar. Okay, so then if we look at the 1 element of this inertia tensor, so I11 is m x x1 square plus x2 square plus x3 square delta 11 minus x1 x1, and we see that again this comes out to be this is nothing but m summation m x2 square plus x3 square, right? So this is summation m p1 square, where p1 is the perpendicular distance from the x1 axis, right? So the perpendicular distance from the ox1 axis is the p1. So we see that this is our moment of inertia about, so this is our ix, the moment of inertia about the x-axis, x, y, z. So similarly, we can see that I22 is Iy and I33 are Iz. And then the off diagonal elements, I12 is they are symmetric. So I12 is equal to I21 is minus summation m x1 x2 and I23 is equal to I32. This is minus summation m x2 x3, right? And then I31 is I13. This is also minus summation m x3 x1. Okay, so these are the off diagonal elements, and as we can see, the diagonal elements are exactly the moments of inertia, and these are the other off diagonal elements are the shear moments or the other second order moments. Okay, so they are they have a negative sign, so they are negative of the corresponding products of inertia. So negative products of inertia. Okay, so then I think I am all out of time, and in the next module we will start with some basic results, some basic examples utilizing this concepts of inertia tensor and the angular velocity tensors, And then later on in another module, we will be talking about the concept of the principal axis and how to find the principal axis through some symmetry rules. So thank you so far for listening.